All right, so we're finishing up today. We're finishing up chapter 2, and that ends with our normal distributions, doing calculations with the standard normal curve, and standardizing scores, finding out proportion under the curve, all those fun things. And then the last thing we'll talk about is assessing normality. Essentially, how can we determine if a distribution is normal so we can use these types of things on that distribution? Because these types of calculations are easier than others. They involve less crazy math. So what I want to start with today is doing normal distribution calculations. All right. We've done some already, and some of you guys did those in the discussion boards from last week. We're going to do some, I'm going to demonstrate some today that are going from an original score to a z-score to a proportion. So there's a couple extra steps going on. So I'm going to show that, how that works. And hopefully this is helpful. What I want to do with this is I'm going to do the example. I'm going to kind of like talk out loud how I'm doing it, what I'm doing. And when I get done with the example, I would like you to ask me questions about what I did. What didn't you understand? What can I clarify? Is there a step that I did that I didn't explain and that you'd like me to explain? Those types of things. So I'm hoping that this is helpful. We'll see. So without further ado, our little introduction here, we can answer questions about area in any normal distribution by standardizing using table A or using technology. We can use our TI-84 to find proportions under a curve as well. That is an option. All right. Here are some examples. So first question here we have on the driving range. Mr. Tiger Woods here practices his swing with a particular club by hitting many, many balls. Suppose that when Tiger hits his driver, the distance the ball travels follows a normal distribution with a mean 304 yards, right, and standard deviation of 8 yards. All right, and so that's what we have over here, right? We have our notation N304, 8, and I've sketched, well, I took a picture of a normal curve from the internet and then wrote the numbers I needed underneath it. We have the mean here at 304 that goes right up the middle, and then standard deviations added to the right, 312, 320, 328, and then 1, 2, and 3 standard deviations subtracted on the left, 296, 288, and 280. Okay, so we have our labeled graph. This is a visual aid to help in what we're doing. I want to know what percentage of Tiger's drives travel at least 290 yards. This means 290 yards or more. So essentially I'm looking at, let's see, 80, somewhere around here. If I can draw a straight line, that's helpful too, but you know. 290 is about right here, so I'm looking for this area. Right? The visual aid is helpful because it tells me a couple things right off the bat. I know that the proportion I have that I get at the end of this is probably going to be bigger than like 70% or 0.7, possibly 0.8. But I know for sure it's more than 50. Most likely it's more than 60 or 70. So if I get an answer that doesn't fit that description, I've made an error. So that's part of why the visual, right, drawing and sketching the curve with where this number falls and all that stuff can be super helpful. It can help identify errors. Okay, so I want 290 or more. I need to find out what the standardized score is for the 290 or more. So that means I just do my standard z-score calculation. We're going to have our 290 minus 304 divided by the standard deviation of 8. Right? This will give us a negative number, but that makes sense because 290 is to the left of the mean. I should get a negative number. That's the other information I get by showing where this point is in my distribution. My z-score should be negative because the yardage I have here is to the left of the mean. That is a negative z-score. Okay. So we've got 290 minus 304. That's going to be a negative 14. Divided by 8. It's going to be a negative 1.75. All right. Now, this is my z-score. If I look this up on my table A, it's going to tell me what's to the left, right? So let's get, I did not open up my table A yet. Let's get that. There we go. Let's do that. Okay. Let's find this bad boy on table A. I'm looking at my negative numbers on table A. I need a negative 1.75. So I'm going to find negative 1.7. And I'm going to go 0, 1, 2, 3, 4, 5. So this gives me 0.0401. Right? That is the proportion to the left of negative 1.75, 0.0401. Move that out of the way. Right, so this is what I get from table A. I want everything to the right. Right? So I'm going to say 1 minus 0.0401. And we get 0.9599. Right? It's asking for a percent, so I can't leave it like this. At this point, I can say approximately 96%. Okay, so that's what I've gotten from this. Now, does this answer make sense? Right? I know that on my normal curve, within 1 standard deviation, right? That's 68%. This adds another, what was it? 68, 95, 95 minus 68. .5%. And then this part is 1.5%, I believe, or not 0.15%. No, I'm not doing that right. 97. There we go. That's what I wanted. 2.35. All right, so if I just look at the standard deviations, I'm going to have 68 plus 13.5 plus 2.35 plus 0.5. That's 84. All right. Does my answer make sense? That's kind of what we want to ask ourselves, right? We want to make sure that what we've done is accurate. Seems accurate. All right, so we have another tool at our disposal here. I can also have the calculator find the proportion under a normal curve. I can do this by going to a vars. Second vars, it gives me a distribution. That's the little blue letters above this. It says DISTR. So I'm right here. I'm going to go to the second option here. It says normal CDF. Hit enter. My lower bound defaults to an excessive lower bound. Essentially, you want depending on what you want, you set one of the bounds incredibly high so that it will count for everything above that number. I only have a lower bound in this case, the negative 1.75. So we're going to put that in. The upper bound I'm just going to put in as an excessively large number. That many, 100,000. That guarantees that I'm going to get any stragglers, so to say. Well, this is on a standard normal curve, right? This is a z-score on a standard normal curve, mean of 0, sigma of 1. Enter, enter. Same answer. So I got the same answer 2 different ways. I'm most likely correct. I can have confidence in what I've just done. We have 0.9599. I got 0.9599, about 96%. Looks pretty darn good. We're going to go with it. So let me say approximately 96% of Tigers drives. If I can spell that out too. Travel at least 290 yards. There we go. That was example 1. All right. What are your questions? How did that work for you guys? That's one example. We're going to do a couple more.
What do we click for the calculator part?
Okay. Sorry. So what you do, let's clear that out. Let's see, can I make this bigger? There we go. We'll hit second and then vars. It's this button here. Right above it in blue letters, it says DISTR, distribution, essentially what it stands for. Then I want the second option, the normal CDF. And we'll hit enter. It's got what I put in there previously already saved, or still in there. I'll show how to use this when you're going between 2 values. This is kind of nice because it doesn't rely on table A and you finding the values in table A. It's another tool, right? You should know how to use table A. So this works kind of nicely as well. The other advantage of this is you can customize it to a mu and standard deviation based on your actual distribution as well, and you should get the same results, right? So I could instead do the 290 yards upper, and I can change this to the 304, right? This to the 8, and let's see if I get the same answer. I didn't try this yesterday when I was planning this, so maybe it won't work very well. Same answer, so that's kind of nice. So this also does not rely on standardizing, which is kind of nice. It will work for a distribution. Don't do this for other distributions, it will not work. It is based on a normal curve. Does that answer your question?
Yeah, thank you.
You're welcome. All right. Let's make this guy a little smaller again. Okay. Excellent. And the other thing I want to point out is that I went through great lengths to check my work. I got a solution, and I wanted to try and justify that solution to myself to make sure I didn't have an error somewhere. So I looked at, okay, what should the proportions be and what I know they are, like in the 68, 95, 99, 7 rule? Does that kind of add up close to where I need it to be? You know, I use the calculator, we use table A. So I'm checking what I've done to make sure I didn't make an error along the way. Because we're, especially as a newer thing that we're doing mathematically, we want to build confidence in our procedures. All right, does anyone need another moment on this problem if you're taking any notes or writing anything down? Can you raise your hand? Okie dokie. So here we are, same distribution again, another question about tiger. And we want to know what percent, so again, we're converting to a percent at the end, of tiger's drives travel between 305 and 325 yards. Okay, so again, we'll make our little picture here. 305 is going to be like not too far off from the mean. We'll pretend my lines are straight. Right? Use your imagination. And 325 yards, which is going to be like over here. So we're cutting off a little bit. Right. So we're looking at this area here. All right. Let's do our standardization first. So I'm going to have 305 minus 304 over 4, or I'm sorry, 8. That's going to be 1/8. 0.125. And so this is my lower bound. The upper bound, we're going to have 325 minus 304 divided by 8. 21. 21 divided by 8. 2.625. So then we pull out table A. There's table A. And we go to our positive z-scores, because that's where this is. And 0.125. So again, so now I'm not going to find 0.125 on my table. I'm going to have 0.12 that I can look at, or 0.13, right? So that kind of inhibits things, right? Same thing with the 2.625. Technically, we should round up because we have a 5 next to the 2 here, and a 5 next to the 2 here. So we'll use 0.13. So we'll have 0.1 here, and 3 is 0.5517. And for our other one, and since we're rounding both up, we should kind of be pretty good. It should work out. 2.6 over here, and then we find the 2, or sorry, the 3. That's 0.9957. All right, so the 0.9957 represents everything to the left of 2.625 standard deviations, and then the 0.125, the 0.5517 represents everything to the left of that point. So to find what's in between, I gotta subtract these things. So we have a 0.9957 minus the 0.5517. And that will give me a number that my calculator will tell me. .444. All right, so that says 44.4%. Okay, and let's check on our calculator, see if we get the same stuff. So we'll again go second, bars. Second option here, enter. We will switch this back to our, well, let's see. We know we can use the numbers. My lower bound is 305, my upper bound is 325. And my mu of 304. Enter. We get 0.4459, right? So this proportion is slightly higher than the one that we calculated using table A. Right? Not a lot. You know, it's basically 44.6 from the calculator. All right. If we, let's see if we get the same thing. Sorry, this is just how I work through these two. I want to see if I get the same scores if I use the z-score, or if I get the same proportions. Yep. So it gives me the same exact score. So that rounding with table A caused a slight error, right? This is going to take into account more decimal places because its calculator has more values essentially saved into its memory than is kept on table A, or at least the table A that we have, all right? However, it just depends on which strategy you're using. Both are going to give you very similar answers. Excuse me. All right, so then in this case, we could say, you know, approximately 44.5%, let's just split the difference, of Tiger's drives travel between 304 and 325 yards. Okay. Any questions? Anything I can clarify? Is this helpful? Maybe. Okay. Last example. All right, we have high levels of cholesterol. Yes, it is helpful. All right, awesome. Thank you, Caesar. High levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal with mean mu equals 170 milligrams cholesterol per deciliter of blood, milligrams per deciliter, and standard deviation sigma equals 30 milligrams per deciliter. What is the first quartile of the distribution of blood cholesterol? All right, the first quartile is the 25th percentile. So it wants to know what cholesterol level, all right, or the blood cholesterol level is at the 25th percentile. So we have to kind of work backwards, right? 25th percentile is going to be at 0.25. That is the number that I look for in table A. All right. When I say in, it's in the interior of table A. It's not the Z numbers on the exterior, it is the interior. I need a 0.25. The 25th percentile will be a negative Z-score because the 25th percentile is to the left of the mean, right? The mean is at the 50th percentile. So this score is going to be in the 25th, somewhere to the left. So we use that knowledge to look at the right part of our table A. I don't need the positive part of table A, I need the negative part. And I'm looking for 0.25 or as close as I can get. So I need to find 0.2. Okay, we get 0.2, 27, 23, 22, 22, 25. Okay, so there we go. We go 0.2514 and 0.2483. Right, we have these two choices here. We have to ask ourselves which one is closer to 0.25. Right. So we have one that's 0.0014 away, and then the other one is 0.0017 away. 2.483 is a little farther away. So we're going to go with 0.2514. Right, this one right here. If we follow that back, that's negative 0.67. So we're at negative 0.67. Right. Right. Does anyone have any questions on how I found that number? Right. So then this is our z-score. Now I need to work this backwards to get the blood cholesterol level. So we set up the z-score calculation just without knowing what that other number is. We have negative 0.67 equals x minus 170, because that is the mean, divided by 30. Right? And we have to solve for x. Right? So that gives us 30 times negative 0.67 plus 170 is going to equal x. Let's put that in the calculator. We get 149.9. So that means, right, and this wants to know what's the first quartile. Right, the 25th percentile, essentially the first quartile of the distribution, is at 149.9 milligrams per deciliter. Okay. So that's weird. All right. Again, we have the graphic here. This one's a little tough, right? Because I don't know exactly where the 25th percentile is going to fall. We can kind of guess-ish, right? 50th percentile is here. Technically, this 25th percentile fell right here, 149, about here. We'll say 149.9 is right around there. So, you know, it's hard to kind of see where that falls on our distribution. We could put it in there afterwards. And then it makes sense. We got a negative z-score, all that fun stuff. All right, what can I clarify? Okay. Does anyone need another moment to write anything down? Please raise your hand. Okay. All right. So then, last thing. There's one other thing we need to talk about, and that is assessing normality. If this one, where did it go? There it is. So hopefully, this should not take very long. So we have assessing normality. Essentially, is a distribution normal? Because if it's normal, I can do all these things that we've been doing recently, which makes stuff easier. We have reference. So why normal? Normal distributions provide good models for real data. We've discussed this, such as the SAT scores, IQ tests, unemployment rates, and so on and so forth. There's many examples. All right, the distributions of some other variables are usually skewed and therefore, oh, I did not spell therefore correctly, distinctly non-normal. This would be considered things like personal income, lifetime of electronic devices, etc. Right? There are things, if they're skewed, they're obviously not normal. It is risky to assume that a distribution is normal without actually inspecting the data first. This is the new key point. We need a strategy for determining if a distribution is approximately normal. So here's a strategy. Is this normal? First, plot the data. See what it looks like. Make a dot plot, stem plot, histogram, something of that nature. Ask yourself, is the distribution symmetric and bell-shaped? No. Not a normal distribution. Yes. Ooh. Check whether the data follows the 68, 95, 99, 7 rule. If it does not a normal distribution. If it does, or if it's close, right? If you get 66%, 96%, 94%, and 98%, pretty darn close, that's okay. Right? This is good evidence that the distribution is close to normal. Notice we don't say, hey, this is definitely a normal distribution. We're not at that point yet, but we have very good evidence to suggest that it is. Hooray! Right? So the first thing is, does it pass the eye test? Right? Does it look symmetric and bell-shaped? Right? Next thing is, let's look and see if our data follows the 68, 95, 99, 7 rule. Right? And you do that simply just by finding, well, I say simply, find the mean, find the standard deviation, and then see what proportion of your data falls within 1 standard deviation, within 2 standard deviations, within 3. If those percentages, those proportions work out, then we're doing all right. All right. Does anyone need a moment to write this down? Lastly, still not sure. We've done these things and we're still like, I don't know. Another way to check for normality is by using probability plots. These are not necessary for you to know. Like, you're not going to be asked to demonstrate a probability plot, most likely on the AP exam, at least that's what the literature has told me. However, it's a way for you to feel confident about saying something is normal. This can be done on your TA84 graphing calculator. Directions can be found on page 125 in the textbook. There's also a video that is in the resources, how to make probability plot. Essentially, it's another plot of your data. So if you've already put your data in to make the dot plot or the histogram, to make a histogram essentially in your TA84, this is another version of a graph that you can get from your calculator using the same list of data that you've already put in. If the points on a normal probability plot lie close to a straight line, the data are approximately normally distributed. Systematic deviations from a straight line indicate a non-normal distribution. Outliers appear as points that are far away from the overall pattern of the plot. Right? on the calculator, this is a probability plot. And this is based on a set of data that I've entered in here on list 1. This is from the textbook. It's the unemployment rate of 50 states. Of the 50 states. And it's already been sorted. Didn't need to be sorted. It's already sorted smallest to greatest. From that data, I need to go to the stat plot. Obviously, this is the one that's already on. We have it turned on, and it is this last option. This is your probability plot. Make sure it's assessing the correct list. If it's set for data axis is X and marked like this, don't change it. It's fine just where it is. To make sure that you will be able to see the whole thing, go to Zoom. There we go. Right here where it says Zoom Stat, basically makes it automatically fit your plot of data. Choose that one, and it plots this. This demonstrates something that should be approximately normal. It creates pretty much a straight line. All right, so this is something else that you could use as evidence to say something is normal.